This is the Chemistry 30 with Mr. Maxwell, and we're going to talk about the Chapter 22 quiz / assignment. Now, this may be the answers to the quiz that you took in class, or these could be the same answers to an assignment that you were given. So I just want to make this video here so that you can watch. These are the answers for the assignment that I've recently given to my class. So I will make these available. I'll just go through each question. The order may be different because there's different versions, but here are the answers to the Chapter 22 assignment questions. A reaction may be spontaneous, but proceeds so slowly that there's no apparent change. The reactants are said to be kinetically stable. Now, kinetic means motion. Okay, so something is stable in its progress or its motion when it's happening under control or happening very slowly. So kinetically stable means it's not very unstable, right? It's not like this reaction will proceed violently and very quickly. It's pretty stable. It may be so slow that you don't even notice it. Question number 2. If a reaction does not spontaneously occur at room temperature, it is said to be thermodynamically stable. So I want to focus on temperature. The first part of this word is thermo, okay? Refers to heat, temperature. Dynamic is movement, right? So the movement of energy. And if something is heat, movement, stable, that means that at room temperature there's not sufficient enough energy to kind of kickstart this reaction. So it's fairly stable. You'd have to apply energy to it in order for it to initialize or to start. Like striking a match. If you have a match and you hold that up, it's not going to spontaneously burst into flames. You're going to have to apply some friction as you strike the match, and that's going to be a spike in temperature to kind of get that reaction happening. Okay, so that's question number 2. Question number 3 says a reaction, and again this might be a different number in your assignment there, but a reaction where products can become reactants again is called a reversible reaction. Pretty straightforward. Reversible. Now, most chemical reactions are not reversible. Think about when you put bread in the toaster and you get that rolling and it heats up and it chars some of the bread, right? It becomes brown. You leave it in there too long, it becomes black. Not easily to get bread back again, right? To undo the reaction that's happened inside there in that burning. So most chemical reactions are like that, but some are reversible. You can have the reactants form products, and then the products can basically disassemble themselves to become the original reactants again. That's a special type of reaction called a reversible reaction. So the reaction rate is the rate of appearance of a product or the rate of disappearance of a reactant. So this is how we measure the how fast a reaction happens. At the rate at which a product basically comes from nothing and starts to be created, that rate is the rate of the entire reaction. Or conversely, if you think about you have the reactants and the rate at which they are decreasing and becoming products, and again it's just the atoms rearranging themselves to become products, the rate of decrease of the reactants or the rate of increase appearance of the product is the reaction rate. Usually the units are something like moles per liter per second, or molarity. Remember, this capital M is molarity, moles per liter. So it would be like the concentration as that increases per second. It's a rate of time. M is molarity, of course, as we talked about. So reaction rate, that's how we define it. Question number 5 and 6. Most reactions take place in a series of steps called a reaction mechanism. Okay, so a mechanism by which something happens are the specific steps in which you go from the start to the end. A mechanism. Okay. The collection of smaller reactions, including the intermediate forms of the reaction, whose sum is the overall reactions. So very seldomly do we have A plus B going directly to C plus D, let's say. Very seldomly is it a one step, okay, or a first order reaction. A lot of the times, A and B will get together and they'll form something else, and then these guys will combine and there'll be other things, and then eventually it'll come back to your final products. And these steps may happen just in a blink of an eye, but there may be intermediate steps and intermediate forms of the reactants as they react. A and B comes together, and for an instant there's this big conglomeration of A and B, and then they separate a different way, and then C and D emerge. So there's intermediate forms and intermediate steps called the reaction mechanism. 6, the intermediate form between reactants and products is often called the activated complex. So as I mentioned, A and B comes together and you have this big, for a nanosecond, you have this activated complex, and as it turns around and separates into C plus D, the in-between part's called the activated complex. And you can read in your Merrill Chemistry textbook on page 548 about that. Number 7, an initial input of energy for a reaction to begin is called an activation energy. Like I said, with the striking of the match, let's say, it's not going to start on its own. You have to apply an activation energy. So energy lower than this activation energy will not start a reaction. If you rub that against your hand, a match, if you rub a match against your hand, it's not going to start, because the friction between the match head and your palm, it does not provide a spike in the energy required to get that reaction going. The slowest part of a multi-step reaction is called the rate determining step. The rate determining step. Just like the weakest link in a chain, right? A chain is only as strong as its weakest link. The reaction is only as fast as its slowest step, if you think about it that way. Number 9, increasing the concentration of one or more reactants will increase reaction rate because there will be more successful collisions. Okay? So if you have some A's and B's floating around here, okay, and these are going in all sorts of different directions, right? They're going to collide, and some of them will collide with enough energy that they will form the products, maybe C and D in this case. If you add a whole bunch more A and B, okay, so there's a whole bunch more A's and B's, then you've got more successful collisions. Okay, so increasing the concentration increases the rate of reaction because there are more successful collisions happening. Number 10, a higher surface area increases reaction rate due to more exposure of reactants and sites of reaction. So let's say we have a big ball of something, and two things are reacting, and we have this big clump of something and another big clump of something. Well, if they bump into each other, you might have this part of one and this part of the other reacting. If these are in thousands of little bits, right? It's all broken up and these all separate. Well, then what happens is the second you have this happening, right? You have all these little things happening, and there's all sorts of little areas where they can, let me just get a different color so you can see this now. So those areas can connect, these can connect, and all of a sudden you have many more sites by which this interaction can occur, and there's more surface area, means that there's more exposure. And let's say a liquid is reacting with a solid. Well, if you have little bits, right, the surface area of those little bits, all around those little bits are going to react at once, instead of just the surface area of the larger one. So everything that's stuck inside is going to be left unreacted for a while. And of course the example would be like Alka-Seltzer tablets, or if you have a big clump of iced tea, right, in your, if you crunch it up, if you smash it into 1,000 pieces, it's going to dissolve quicker, or just like in a reaction would react quicker. A catalyst, number 11, increasing the temperature of a system increases reaction rate because more reactants will have sufficient kinetic energy. So particles will literally be moving faster, so they'll have enough energy to kickstart the reaction. If something grazes, if two particles graze each other, they may not react. But if they slam into each other, they will react. So think about it that way. A catalyst is a substance which causes an increase in reaction rate without itself being permanently changed. So the catalyst is just sort of something that comes alongside and helps the two get together. Kind of like if you're introducing your two friends, right, together, and you say, hey, Jimmy, you'd really like Sally over here. Why don't you guys come meet at my place, and we'll watch a movie or something, and you guys can connect. And so you are the catalyst, right? They might run into each other somewhere in the world at some point in time, but you are the catalyst. So you are not yourself being involved in the relationship, but you are bringing them together. So you're like a catalyst in that situation. So there are chemicals and substances that can act in the same way, bring two things together, or provide something or an atmosphere of something that would make this reaction happen quicker. That's called a catalyst. So number 13, reaction rate is affected by the types of reactants involved. That's obvious. This factor is referred to as the nature of the reactants. Okay, so the nature of the reactants affect the reaction rate. just by their chemical properties, physical properties. Different things involved will react in different ways. 14, increasing pressure or temperature would fit in this blank of a gas increases its reaction rate. So if we're talking about a gas, if you increase the pressure in the system, or if you increase the temperature, or number 15 says also for a gas, if you decrease the volume, all those things will increase reaction rate. So you up the pressure, then there's more force happening, and these particles bump into each other. Increase the temperature, they move faster. Decreasing the volume literally decreases the amount of space that they have to avoid each other, right? If they were indeed avoiding each other. But if you have if you have two balls and you're in a classroom and you throw those balls around just randomly when you're blindfolded, they may hit each other after a few minutes. They may not hit each other after an hour of throwing the ball around. But if you and a buddy are in a closet or in the bathroom or in a smaller room and you're randomly tossing the ball around, they're going to hit each other a lot quicker, right? So that's decreasing the volume. And finally here, if a equilibrium constant is large, now we're going to talk more about this in future videos, the equilibrium constant and what even equilibrium is. You don't really know much about that yet. But if the equilibrium constant is large, then the production of products is favored, okay? Oh, and this isn't the last question, but we'll talk more about equilibrium as we move through this. I think there are two more that I have here that I want to talk to you about. So 17, if a chemical slows down a reaction process, it is called an inhibitor. So to inhibit something means to hold it back. So if we're holding back the reaction, we are inhibiting it. There are certain chemicals that are used as preservatives for food, so the food doesn't spoil as quickly. Those are inhibitors, okay? In the presence of this chemical, this certain reaction that would be a decay or a rotting of food wouldn't happen, or it would at least slow it down and get in its way. That would be an inhibitor. And finally, this last question that I have here, if at equilibrium the concentration of reactant A is increased, the system or the reaction as a whole will counteract this stress by generating more product. This refers to Le Chatelier's principle, which again is another concept we'll be talking a little bit more about a little bit later. But if you have two reactants and you increase one of them, it would make more sense that there's more reactant involved, and that will also the reaction rate will increase, and there will be more of some product made then, right? If there's more reactants available, there's going to be more products made. So that's number 18. So the next video that you want to watch here is the instruction on the rate constant. That's what comes up next in the notes. So rate constant is going to be your next video that you're going to want to watch in this chemistry series. Okay? God bless.